In this video, I'll be demonstrating how to set up and align a Fabry-Perot interferometer. For our Fabry-Perot, we're using custom-made mirrors that consist of a 1/2 inch round of fused silica, with one side with a radius of curvature of 75 millimeters, and the opposite side is flat. On the curved side, it has a reflective coating with a reflectivity of around 98 to 99% between the wavelength range of 820 nanometers to 960 nanometers. And the back side is coated with an anti-reflective coating within the same range. We've mounted our mirrors on standard mirror mounts. In one mirror, we'll mount directly to the optical table, and the second mirror will mount to a stage that has a piezoelectric actuator in it, such that we can scan the length of the cavity and create a scanning Fabry-Perot interferometer. Now, for demonstration purposes, we're using open Fabry-Perot cavity. An open cavity is susceptible to many different types of instabilities, such as air currents or thermal instabilities, but for demonstration purposes, it's satisfactory. Now, to guide the beam into the cavity, we'll be using 2 steering mirrors. And for mode matching, while there's several different techniques for mode matching, we'll be using a technique that utilizes a single lens. In this technique, we have our source that comes from an optical fiber, and we position our lens such that it focuses to the correct size that the cavity supports, and then we can set the length, the path length, such that the focus is at the center of the Fabry-Perot cavity, and to finally adjust, we can use a stage. Now, we have a few other tools that we'll be utilizing. We'll be utilizing a camera to view the spatial modes, along with a monitor. Obviously a function generator to divot the length, and then to view the transmission of the modes, we'll be using a photodiode along with an oscilloscope. Now, the first thing we have to do is go over some mathematical estimates to direct our setup. Constructing a Fabry-Perot interferometer, there's several different parameters one can choose based on the desired outcome and needs of the interferometer. In our case, we already chose our mirrors, so what we have left to choose is the length of the interferometer, or the separation between the 2 mirrors. Now, we desire a free spectral range, or the separation in transmission peaks in frequency, of around 4 gigahertz. We can use this to find the length of the interferometer by setting it equal to an approximate formula for the free spectral range, which is just the speed of light divided by 2 times the length. And this gives us a length around 3.75 centimeters. Now, for our reflectivity and our free spectral range, this gives us a resolving power of 25 megahertz. The second thing we need to calculate is the beam waist of the Gaussian beam that our interferometer supports. Now, in our case, we can neglect the thickness of mirrors and use this formula that we obtain from laser beams and resonators. And this takes in a radius of curvature of 75 millimeters, a length of 3.75 centimeters, and a wavelength of 920 nanometers. And this gives us a beam waist, or W naught, of 100 microns. Now, the third thing we need to calculate is the separation between the lens and the fiber, and the lens and the center of the interferometer. Now, in our case, we can use the lens maker's formula, where S1 is the separation between the lens and the fiber, and S2 is the separation between the lens and the center of the Fabry-Perot interferometer. Now, to get Y1, we can use the mode field diameter of the fiber, which in our case is a Thorlabs SM800 5.6 125, which gives a mode field diameter of 5.6 microns, and just divide that by 2 to get Y1. Y2 is our calculated beam waist, which is about 100 microns. And then to get F, our focal point, we can use our part number for the collimator that we're using that has a lens in it, which is the Thorlabs CFC8XB, which has a lens in it of a 7.5 millimeter focal length. Alright, now we can solve for S1, which is approximately 7.7 millimeters, and now S2, which is approximately 275.4 millimeters. Alright, now we can construct an interferometer. Alright, now we're ready to set up our system. It's always good practice to make sure your optical elements are around the same height. That'll make it a little easier to align the vertical angles. So the first step I have to do is I have to set up the Fabry-Perot, right? So we have one mirror already secured to a stage that has a piezoelectric actuator in it. So we just have to secure the second mirror. Now, from our calculations, we want the second mirror approximately 3.75 centimeters from the first mirror. So I can just use a ruler to measure that. And since we're using curved mirrors, we can just visually align these since the alignment requirements are much less stringent than flat mirrors. So it's about 3.75. So I'm just going to attach this mirror. Alright, so the mirror is pretty well attached. Now the second step is I'm going to have to adjust this this lens such that it focuses down to around 275 millimeters for our wavelength, which is around 920 nanometers. So I can view the beam on a card, a viewing card, since we can't see the near infrared with our eyes. And now that I know that it's starting out, in our case we're starting with a collimated beam, which means that essentially it's focusing to infinity, which means that the lens is approximately the focal distance from the source or the tip of the fiber. So that means it's around 7.5 millimeters from the fiber, so I just have to adjust it further away from the fiber to get to approximately 7.7 millimeters, which will focus down to 275 millimeters. So I'll just do that. Alright, that looks good. I'm just going to measure from the center of the Fabry-Perot to this guiding mirror about 100 millimeters. There we go. And between this guiding mirror and this other guiding mirror will be 75 millimeters. And then from this guiding mirror to the lens is 100 millimeters, which totals are 275 millimeters. Now I'm going to loosely attach all these optical elements such that I can coarsely adjust them still. Alright, so to make the alignment, the coarse alignment just a little bit easier, I'm using a red alignment laser. This is easier because obviously we can see the red, but also the red laser will directly pass through both mirrors because it's not reflective at that wavelength. So I'm just going to adjust this so it hits the first guiding mirror in the center, and then adjust it so it hits the second guiding mirror in the center. Alright, and adjust the second guiding mirror so it hits the first Fabry-Perot mirror in the center. Alright, there we go. So now I'm going to do a rough walking the beam procedure where I adjust the first guiding mirror such that the beam is at the center of the first Fabry-Perot mirror, and then the second guiding mirror such that the beam is at the center of the second guiding mirror, or second Fabry-Perot mirror. There we go. And there we go. Just make sure, come back a little bit. Alright, so this looks pretty good now. Now I can firmly attach all the optical elements. Alright, so lastly, while the red beam is still here, I'm going to introduce this viewing camera using the red beam. Positioning it so the red beam's at the center of it. Alright, now we're ready to reintroduce the 920 beam and finally align the Fabry-Perot. So I reintroduced the 920 nanometer laser into the system, and we're currently viewing the transmission from the camera on this screen while simultaneously dithering the position of this mirror and hence dithering the length of the cavity. Now, as we can see on the screen, it's this weird oval shape in transmission. So what we need to do is we need to adjust both these two guiding mirrors such that this oval shape collapses down into a singularity, or a dot. Now, in order to do this, we're going to use this procedure, this walking the beam procedure that we've used in several other videos, where we move one mirror and then compensate for the other. And we do this both in the horizontal and the vertically separately. So how I'm going to start this is I'm going to adjust this closest mirror such that this thing kind of collapses in on itself a little bit and we start to see these fringes. Alright, so now I'm ready to start with this horizontal alignment. So first I'm going to move the closer mirror, and then I'm going to compensate with the other mirror and bring it, move it out and then bring it back. And I'm going to keep doing this, and I notice that this is actually getting wider, and also that these fringes are becoming less and less, or more and more vertical and not horizontal. So basically I'm going the wrong direction, I know, so I'm going to move these mirrors the opposite direction. Move it away, then realign it, move it away and realign it. And now I'm noticing that these fringes are getting more and more horizontal and this line is getting smaller, so I'm going to keep going in this direction. Alright, so alright, that looks like I've gotten to the best alignment for the horizontal right now, because these fringes are horizontal and this thing has collapsed. If I keep going, it'll start getting more and more wider, and the fringes will be less and less horizontal. So I'll go back to where I was before. Alright, so I'm back to where I was before. Now I'm going to move to the vertical alignment. So adjust one and then compensate with the other. And it looks like I'm going the wrong direction because it's spreading out, so now I'm going to go the opposite direction with these. And it's getting closer, but it's also, slightly misaligning the horizontal too, so we're going to have to readjust the horizontal, but there you go. So I've collapsed this down a little bit, and you can see the fringes are kind of vertical and kind of circular, so we're getting closer. Now I'm going to go back to the horizontal and do the same thing. So it's actually starting to get wider, so I think I either went past the point or was going the wrong direction, so I'm going to go back. Alright, so again it's back to its smallest point, so I'll go back to the vertical alignment and do the same thing. So it's getting bigger, so I need to move back the opposite direction. There we go. I'll adjust the horizontal a little bit. Alright. So now I'm just making some fine tuning adjustments. Alright, so now you can start to see that these fringes are actually turning into a donut shape instead of horizontal or vertical lines, right? So that means we're getting much closer. It also means, though, that we're coupling into other modes of the cavity, right? Because the fundamental mode is a solid dot, and the higher order modes are these different donut-shaped modes that have a ring. So in order to view this, I'm going to slow down the scanning so we can, individually view all the modes. As you can see, there's several different higher order modes, but we also get the fundamental mode, you see there. So we're close enough that we can move on to viewing the transmission on a photodiode on the oscilloscope. So I'm going to speed it back up again and then introduce the photodiode. Alright, so if we take a look at the oscilloscope trace, you can see a couple things I'm displaying. One, the voltage from the photodiode, which is the transmission of the cavity. We can see that we have the fundamental mode, and then we have a couple of higher order modes. And then back again to the fundamental mode. And I'm also displaying the voltage sent to the piezo, which is scanning the cavity length over a range that includes two fundamental modes, which means I'm scanning over a range of approximately the wavelength divided by 2, or in our case 460 nanometers. Another thing I'd like to point out is this pattern, right? This pattern of the fundamental mode and then the higher order modes of the fundamental mode is periodic. So if I change the offset length of the cavity, I get back to the original pattern, right? So I've changed it another 460 nanometers, and I can increase it another 460 nanometers and come back to the same pattern. Alright, so we can use this oscilloscope trace to determine how well the light is coupled into the cavity. We can take a look at a couple of things. First, we can take a look at the size of the fundamental mode compared to the higher order modes. In our case, we can see that it's at least 8 times higher. The fundamental mode is 8 times higher than these higher order modes, so that's pretty good. Another thing we can compare is the transmission through the cavity. So before I set this up, I measured the inputs, the intensity of the input light into the cavity, and I marked it with the oscilloscope's cursor. And we can see that our transmission peak reaches about 75 to 80% of the input light. So that's another good thing to compare when looking at how well light is coupled into the cavity. Alright, as a final step, we're going to calculate the reflectivity of the mirrors using the transmission through the Fabry-Perot. Now to do this, we took an oscilloscope trace of the transmission through the Fabry-Perot while scanning the Fabry-Perot's length such that it went over 2 resonance peaks. This way we can use an estimate for the finesse, which is the ratio of the peak separation over the full width half max on one of the peaks, where we got the full width half max by fitting a Lorentzian into one of the peaks. This gave us a finesse of approximately 180. Now we can use the relationship between the finesse and the reflectivity of the mirrors to calculate the reflectivity. Now, we further simplified this equation by setting the square root of r to 1. This way we can solve for r, which gives us a reflectivity of 98%, which is within the stated reflectivity of the mirrors. Alright, finally I want to go over some concluding remarks. First off, we made a couple assumptions and simplifications when calculating the mode matching parameters. Most importantly, we ignored the mirror thickness and curvature. To get a better idea of how to include this, you can see the paper I mentioned earlier, laser beams and resonators. Second off, for the mode field diameter, we used an approximation from the Thorlabs website. Now, this is an approximation, and it also is wavelength dependent, and we did not adjust for wavelength. Now, to better adjust for these two parameters or to get better mode matching, one can optimize experimentally by adjusting the position of the lens and then realigning the Fabry-Perot and iterating this process until they get a maximum transmission. Approximately a good rule of thumb is around 90%. But this was too long for our video. Now, secondly, I want to mention that for demonstration purposes, we used an open Fabry-Perot that was just attached to the optical table. Now, if one were wanting to make an actual instrument, one would have to use rigid spacers between the mirrors to help minimize the mechanical vibration, and also they'd have to make it temperature controlled to eliminate thermal drift. Thirdly, we used curved mirrors in our Fabry-Perot, which are much easier to align or much less stringent to alignment than flat mirrors. Now in this case, you can see from the video, we just visually aligned them and it worked with curved mirrors. Now a rule of thumb is, the smaller the radius of curvature, the easier the Fabry-Perot is to align. But there's also a restriction where this has to be within the region of stability of the Fabry-Perot. And in order to do this, the length must be less than or equal to 2 times the radius of curvature of the mirrors. Alright, so this concludes our demonstration how to set up and align a Fabry-Perot. I hope you find it educational and informative, and thank you for watching.